Hello there and welcome to our project presentation. We are Mustafa,
Einar, and Mikael.
And in our project, we use deep learning techniques to recognize human actions performed in videos like these. This is the KTH Actions dataset. There is an astounding amount of video data in the world. On YouTube alone, people upload 500 hours worth of content every minute. This could potentially be a goldmine for training advanced deep learning models, especially models of human behavior. However, dealing with video data is not an easy business. The first obstacle one has to overcome is designing and implementing the input pipeline. Videos come with a third temporal dimension, which can vary in length and does not allow for a simple way to resize their durations like we can do with images. We solve this by allowing our videos to be of varying durations, but we randomly sample a set number of consecutive frames from them. So now, how do we use these frames to recognize the actions in them?
Now, we know that humans are often capable of recognizing an action from a single picture. So can we get a neural network to do this as well? We put this to the test by leveraging transfer learning to fine-tune a pre-trained convolutional model. The model we use is based on Inception v3 that's been trained on ImageNet data. We replace the output layers and unfreeze some of the convolutional layers, allowing us to retrain it to our frame data. It's worth mentioning that we try to keep the output layers as simple as possible and also use some regularization in order to control overfitting. The reason we do this is because we would like to later use these models as feature extractors. This naive approach delivers okay results, but they are far from satisfactory. The KTH Actions dataset has 6 different actions: boxing, hand clapping, hand waving, walking, jogging, and running. Now, obviously, when classifying on a frame-by-frame basis, some of these actions can look very similar to one another. For example, jogging, running, and walking all feature very similar shapes. This is one explanation of the poor performance of the approach we just used. This is also confirmed by taking a look at the confusion matrix.
What we learned from the above method is that we miss all information hidden in the third temporal dimension. But this is what makes video special in the first place. To take advantage of this valuable source of information, we try out 2 different strategies. In our first approach, we exploit the aforementioned Inception v3 model as an extractor of special features. We then take these special features, given as vectors, and treat them as a sequence of data, which in our best model are fed into an LSTM that now learns the temporal dependencies between the frames. These, indeed, yielded much better results, as we see in the confusion matrix, where the number of mismatches is much lower. But so far, we have handled the treatment of spatial and temporal features separately. For this very reason, our second approach takes a different angle. Here, we use 3-dimensional convolutional neural network with 4-dimensional filters that can traverse through time, as well as height and width, as presented in the illustration. The architecture of our 3D CNN is very similar to often used image CNN architectures. It is worth mentioning that the classification in the last layer is done by minimizing an SVM loss. The end results show indeed that the 3D CNN achieves an accuracy of around 92%, which is pretty performant.
But how robust are these networks in the real world? Well, the KTH Actions dataset has several empty frames where no actions are performed. These are left there deliberately to make the networks more robust in the real world. However, the dataset also comes with the markers of where these empty frames are. We tried out the robustness of the networks by trimming away these dead frames and training the networks on the trimmed versions of the dataset for the sake of comparison. As we can see in the final results, the 3D CNN is the most performant on the trimmed data. However, it also seems to perform badly when trained on the untrimmed version of the dataset, which might indicate poor robustness in the architecture. Therefore, the overall winner is the fine-tuned Inception v3 with the LSTM. And now, for the final reveal, we will show you how it actually performs in the real world. Here you see me performing the different actions that Einar mentioned before. It's worth mentioning at this point that what you see here is the color images, but what we actually feed the network is the black and white and downscaled version. So the first thing I try is actually to jog, run, and walk. The first 3 that were a bit ambiguous for the network. Now, when I stop to do the stationary, more distinct action, we see the network begins to shine. And here I will let you observe its predictions.
Mustafa mentioned previously that there are some extra challenges involved when dealing with video data, but these results clearly show that it is well worth the effort. By considering videos instead of single frames, we're able to boost the accuracy from about 65% to 90%, a major improvement. Now, video-based learning might hold the key to great advances in artificial intelligence, but it might also be used for ends such as mass surveillance. It is clear then that we need to at some point have a discussion about the long-term consequences of this technology. Thanks for watching.